Hey guys, this is Mr. Krenz, and in this video I'm going to talk a little about regression. Now, regression is a statistical technique for fitting a relationship to a given set of data. In this video we're going to talk about two specific types of regression. That would be linear and exponential. Okay. Now, if you haven't worked too far through this unit, you may need to go back and either learn a little bit more about these topics, or maybe go review. Exponential is going to look something like y equals mx plus b, so it'll be linear, and exponential is going to look like y equals a times b to the x. All right. Basically, the big difference is that linear is going to be something that's adding or subtracting the same thing every time, and exponential is going to be something where you multiply by a number at the same time. All right. So let's just jump into the first example. We have the set of data. It's graphed for us. We see some points coming down here. Looks like it curves down and kind of smooths out there. And then we have the data given to us also in a table. And what we want to do is determine whether we think this relationship is linear or exponential in nature. Give a reason why, and then also give an equation that fits that relationship as well as possible to the given set of data. All right. Now, looking at the graph, it looks pretty clearly like this data is not linear because it curves pretty big. And we can also look at the table and see, okay, is there something in the table that would tell us that this data is exponential? To do that, what I'm going to do is look and say, okay, well, it drops by 5, and then by about 2 point something, and then about 1 point something, and then about 1, and it kind of keeps dropping down there. We want to see, is the quotient the same here? So when I do 5.4 divided by 10.62, that comes out to, let's see, a polygraphic calculator. No reason you have to do this in your head. See, 5.4 divided by 10.62 be about 0.51 around. Right, if I divide those guys, 3.08 divided by 5.4 gives me about 0.57. Pretty similar number. If you keep going, 1.88 divided by 3.08, get about 0.61, a little bit bigger. 0.67 divided by 1.88, get about 0.36. All right. And what you can see here is that it is staying roughly similar here. Let's do that one last one. 0.01 divided by 0.67. All right, and that one is a little unusual there. Okay, but for the most part, we're sticking right around this middle area. Maybe about 0.5 seems to be about the center. So what I'm going to do to see if this is actually going to look at that is I'm going to enter all this data into my calculator. The way I do that is let me move this up a little, hit the stat button, we're going to edit, and we're going to enter all this data into list 1 and list 2. Get arrow over to list 1, arrow up, hit clear, and then enter. That'll empty that out. The same thing for list 2, clear, enter. Now I'm going to enter my x's as list 1 and my y's as list 2. So 0, 1, 2. Alright, and then list 2, we got 10.62, 5.4, 3.08, 1.88, 0.67, 0.01, 0.05, 0.58, 0.06. Alright, and now what I'm going to do is run a regression. Okay, to do that, we're going to hit stats, I'm going to go to calculate. Arrow over to expreg, it's exponential regression. Right, I'm gonna give it list 1, comma, and list 2. Now to get to this L1, L2, I'm not typing in L1 and L2. Hitting the second button and then finding L1 and L2. What I mean is run an exponential regression with L1 as the x's, L2 is the y's, and I'm even going to store it into a function. So hit vars for the variables, on the y variables, and I'll store this in the first of my functions. And I'm getting a domain error. Let's see, I can go to something wrong with this. Let's see what's happening. Go back and look at my data, make sure that my data is set up correctly. I wonder. So I changed that 0 right here to be a 0.01. I'm going to rerun what I did. Okay, and it worked that time. So I'm going to change that to 0.01 and put a star next to it. And we're going to go back and talk to it. So what this has done is it said, okay, for this data, here is a pretty good relationship. Y equals A times B to the X with this A and this B. Let me write that down. So you get Y equals, so substituting in here, 5.96 times 0.54, we'll round that, to the X power. Okay. I'll take a look at the graph to see how well this fit the data. I hit zoom, and I go to zoom stat.
The science department is late for their meeting. Please report to room 332. That's the science department meeting in room 332.
All right. And it looks like this curve actually fits this data reasonably well. Not perfectly, but it's a pretty good description of what's happening here. Now, the reason that we saw an error there and when I had this 0 is because if you look at the equation, y equals a times b to the x, all right, if this is a fraction, multiplying by a fraction over and over and over, it's going to keep decreasing and decreasing and decreasing, which is why we see decay here. However, no matter how small that gets, the y is never going to be 0, and our calculators can't quite handle that. So I changed that value to be just something very, very, very close to 0, not 0, and that made it work. All right. So let's sum up what we've done here. Is we first looked at the data and said, okay, it looks kind of exponentially. We looked at the table and said our quotients are relatively constant, 0.51, 0.57, 0.61, 0.36. They're not perfect, but they're, this one looked a little funny here. But they're relatively consistent. We ran an exponential regression on our calculator. Did that by hitting stat and edit to enter data in list 1 and list 2. And then we hit stat, went over to calculate, and ran a exponential regression. That spit out some data, and we got this equation. So, see, that was our exponential relationship. The reason why was the quotient of consecutive y values is relatively constant. Right. Alternatively, you might say, instead of dividing, say, okay, what the number it takes me to multiply by 10.62 to get 5.4 is about 0.51. To get from 5.4 to get 3.08, you multiply by 0.57, and the multiplier you need each time is relatively similar. Okay, and then this equation right here is a pretty good description of this curve. All right, now let's take a look at a second example here. This one, even though there is some bumping, it seems like it may be just a little wavy. It seems like it'd be relatively well fit by a straight line. To look at that, see if that's confirmed in the data, we look at the differences here. All right, to get from 4.06 to 4.75, you'd have to go up. Let's see, that would be 0.69. Now to get from here to here, you're actually going down 0.15. And here you're going up 0.09, and just go through overall and see, does there seem to be a pattern? Whoop, I skipped one there. Down 0.01. The next one. Yep, plus 0.75. plus 0.84 plus 0.37 and to be minus 0.37 and plus 0.78. Right. Now, in any data we have that arises from natural circumstances, you're going to see a certain amount of noise, a certain amount of variation. The question is, overall, do we see a relatively consistent pattern as we increase our x's by 1? And I argue yes. We got 0.69, 0.75, 0.84, 0.78. And we got some lower ones in here, but it seems like it's marching up by about that or so. So I'm going to say that this is a linear relationship because it's not perfect, but overall it seems there is a relatively constant increase in the y values. All right. Now to run this regression, I'm going to do basically the same thing as did above. Pull up my graphing calculator. I'm going to enter my data in. So second, hit stat and edit. I like my x's already, so I'm not going to actually bother with changing list 1. But list 2, cleared up. 0.0. And now just some data entry. All right, make sure that my lists are the same size. Here they are. Now run a linear regression. I hit stat, over to calculate. I see linear regression here. It's being ax plus b. Instead of mx plus b, they use ax plus b. Hit enter. All right, I'm going to do the same thing as I did last time. So second list 1, second list 2 for max and my y's. I'm going to store this all into a y variable. So hit vars. Over to y variables, choose function. I'll choose the first y one. Hit enter. All right. Now this time we have y equals ax plus b, and it gives us an equation of 0.32 x plus about 3.99. All right, now let's look at that, interpret it for this picture. Actually, I can take a look at my graph, hit zoom, and zoom stat. Zoom stat's nice because it automatically changes the window size to fit our data. All right, and that looks like it fits our data very, very well. Okay, now let's look at this whole thing, kind of interpret what's happening here. This right here would be my slope. And that's saying for every time I increase the x value by 1, like I am in this table, the y value is increasing by roughly 0.32. Okay. Now if we look over here, it looks like there's like 0.69, 0.75, 0.84, 0.78, and then I also have some very small ones. You know, that was actually negative. That one's actually negative, basically 0. This is very close to 0. If you kind of average these out, look in the middle, basically between 0 and 0.69, you're around 0.35. And we had two that were very close to that value. All right. So yeah, there's a lot of variation here, but we see a steady increase. Looking at the graph on our calculator, looks pretty good. And so now we can interpret what these things mean. This would be about the slope or the rate of change. And then this guy would be our y-intercept. Right. So just a quick bit of review, kind of what we've done here. Regression analysis is a statistical technique for fitting a certain relationship to a set of data. Okay? If the data looks like there's some kind of curve and it's either growing exponentially or decaying exponentially, you might take a look at the quotients or what constant multiplier you might need. You can enter the data in your calculator and you can run the regression. Right? Alternatively, if the data looks roughly linear, still the same kind of thing. Enter the into calculator. Check that you think I'll probably use a linear regression here because the change in the y value seems to be relatively constant. Run the regression and you get a best fit equation.